action. Hello and welcome back to Calculus 1, section 3.5, derivatives of trigonometric functions. So far, we know derivative constant is 0. We can deal with polynomial functions, radical function, rational function. We have a product rule, quotient rule, constant multiple, and sum difference. So now it's the time, and e to the ax, right? So now we are going to go into the realm of trig functions. There are 6 trigonometric functions to deal with. And the first one is going to be sine functions. So derivative of sine x is going to be cosine x. Now, there is a proof that I could work out now, and there is another much better proof in Calculus 2 in chapter 9 that you guys will eventually see if you go to Calc 2, obviously. Now, the proof for this is actually done like all other proofs for derivatives using the difference quotient. Except this one is more interesting because we have to use the sum and difference formulas for trig, and then we have to define 2 limits that we have to use now, but we are not going to. So we have to use those 2 limits, and we have to know their answer without being able to compute those 2 limits, which means, you know, you have to take it on faith on that one until chapter 4, and then you will know how to do the limit and so on. So one of those limits for the proof would be that the limit x goes to 0 of sine x over x is equal to 1. I did mention this limit before, and this limit was supposed to help you. I mean, the solution for this limit you were supposed to have available in chapter 4. So now we are going to write one more of those, which is the limit x goes to 0 of cosine x minus 1 over x is also equal to 0. So these are the 2 limits that you will be able to compute in chapter 4. It's 4.7, I believe, section. But for now, you just take them as given and so on. So now, we haven't really proved any of the previous ones, so let's just do for sine, and then the rest you can play with if you want to. We know that we do the limit h goes to 0 of sine x plus h minus sine x over h. So this is our job. And what I can do, the only thing that I can really do is to deal with the sign of the sum, right? So I can go limit h goes to 0, and then over here I have sine x cosine h plus cosine x sine h minus sine x divided by h. And I'm going to take first and the last term and factor out sine. So it's going to be sine x, and then I have cosine h minus 1 over h. And then in a separate limit, I'll put limit h goes to 0, cosine x sine h over h. Now, I hope you see that this part over here was that special limit we defined as 0, right? And this part over here is this another special limit up there, which is defined as 1. So the first term dies, and the second term is just, cosine x times 1. So the whole thing is cosine x. So this would be the proof, right, using the sum of angles and those 2 special limits, right? to solve it. So now that we have that the derivative of sine is cosine, you can do the same procedure and figure out the next formula, which says that the derivative of cosine x is negative sine x. So that's your next formula. What's left? Well, what's left is the derivative of tangent. How would you find the derivative of tangent x? Sine over cosine, and use what? What do we use? What do we use? We just learned it. Quotient rule, exactly. So let's go. Quotient rule, we have denominator squared, so it's cosine squared x. Copy denominator, derivative of the sine is negative, derivative of sine is cosine. Oops. Derivative of sine is cosine. And then minus copy sine. This is not going to fit there. From scratch, the next line. So we have cosine squared x, then we have cosine x times cosine x minus sine x times negative sine x. There we go, much better. So in the numerator, I have cosine squared x plus sine squared x divided by cosine squared x. What does this give me? No? What's cosine squared plus sine squared? Oh, it's 1. Okay, fine. So it's 1 over cosine squared x. And what's 1 over cosine? Very good. So now finally, I can write the formula for tangent x, which is secant squared x. Nice. What would you do to find the derivative of secant? No, secant is not cosine or sine. Secant is what? 1 over cosine. And then do what? All right, do the quotient rule now. Go on. All right, so let's see. We said cosine squared x in denominator. Write cosine x times 0, because derivative of 1 is 0. And then minus 1 times, and derivative of cosine is negative sine x. So now, the first term drops. The second term is just sine x. So all I have is sine x divided by cosine squared x. What I'm going to do is split this into 1 over cosine x times sine x over cosine x. 1 over cosine is secant x, and sine over cosine is tangent x. So what we learned from this calculation is that the derivative of secant x is secant x tangent x. So if you know sine and cosine formulas, you will be able to compute other 4. However, these formulas are awesome because they are very symmetric and very easy to memorize if you spot the patterns and just go from there. So what I want to do is write the summary for all of these trig formulas, and then we can do a few examples. Now, again, guys, for these trig formulas, product rule applies, quotient rule applies, all of the sum and difference from before, and then we can do the tangent line problem just like we did before. So now let's first put all of the formulas on the pile. The derivative of sine x is cosine x. And on the side over here, I'll say that the derivative of cosine x is negative sine x. Now below, I'll say that the derivative of tangent x is secant squared x, and that the derivative of cotangent x is negative cosecant squared x. The derivative of secant x is secant x tangent x, and finally the derivative of cosecant x is negative cosecant x cotangent x. So this is the summary of all trig derivatives. Now we are going to have a separate section, I believe it's 310, on inverse trig derivatives. That's a completely separate section. This is just for the trig. Inverse trig are different functions. So now that we have all of these, let's take a look at the symmetry between these to make sense of what we do. First off, can you all see that if the trig function begins with it's going to be negative, right? It's cosine, cotangent, and cosecant, right? So if it starts with the it's negative. We good on that one? Now also observe trigonometric pairs. Sine is always with cosine, secant is always with tangent, and cosecant is always with cotangent. There are no crisscross between them, right? So let me write that over here in blood. So trig pairs sine, cosine, secant, tangent, cosecant, cotangent. All of them work the same. And finally, just take a look that the left and the right always have the same form. The ones on the right being negative. Sine and cosine, cosine and negative sine. Tangent is secant squared, cotangent is negative cosecant squared. Right? So if you know the pairing and you know one side, the other side is going to be symmetric. So I hope you see all of these connections. And now, what can I ask? Well, simple questions, like what is the derivative of tangent, what is the derivative of 2 times tangent, what is the derivative of tangent divided by secant, what is the right, and then you just, you know, have the product rule, quotient rule, and all of this, and then finally find the equation of the tangent line if blah, 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 and you still have to take the derivative. So let's take a look at some of these. Really, but there is something interesting. Let me start there, because we haven't addressed this much. Find 136th derivative. You got this. Of sine x. Now, obviously, you know that you have to go in order. So let's start taking derivatives and see. Don't you love it? This is the first example. Now, we got time to go 136 derivatives. So let's get busy. It's amazing how that clock went from being approximately correct to being exactly correct twice a day. What? You have a clock, it's never exact. Never. But when you have a clock with stop, it's exactly correct. Okay. Did anyone figure out the way to do this? Yes, it loops every 4. Very good. So if you took 8 derivatives, which is really quick, right? If you took 8 derivatives, you spotted a pattern. So the way to solve this problem is to literally divide 136 with 4 and figure out what is the remainder, and you're done. So we start with that function f of x is function f of x, no, f prime, sorry. First derivative is cosine x. And then the second derivative, 2 tick marks, right, is negative sine x. Then the third derivative with 3 tick marks is negative cosine x. And now for the fourth derivative, notation changes to parenthesis, and we go back to sine x. Now if you're taking the fifth derivative, sine is again cosine x, and you see it's the same as the first. And then it loops. It will go and have the same derivatives, and you can do this forever. Well, you can't, but because you're going to die eventually. So as you go, you see that each one of these, right? So now, what's the 136th derivative? Well, it's 136 divided by 4. That's going to be 4. And it's going to be 12. No, it's going to be 3. 3 times 4 is 12. And then 14. 4. And remainder 0. So, remainder 0 is, so it's sine x. So, 136th derivative of sine x is itself sine x. Remainder 0, this is where the remainder 0 is. This is remainder 1. When you divide by 4, 1 is left over for 5. When you divide by 4, 2 are left over to 6. 3 are left over to 7. And 0 remainder for 8. So if the number divides evenly, that falls into these category. And all of these answers are always sine. All of these are always negative cosine and a negative sine and so on. So it falls in somewhere, right? Now, there is a reason for this, clearly, for this to be looped like this. If you study mathematics a little bit, to those of you that are interested, I'm just going to drop a definition on the side, and then you can go and figure it out. And that definition says that the sine x is defined as e to the ix minus e to the negative ix over 2I. Now, I is that square root of negative 1. It's a complex number. And that one loops when you have the powers of it. Now, these are e's. You know that what happens with e's. As you take the derivative of e, the number a in front of x, in this case is I, drops in front of e. So what do you get? You get I squared, I cubed, I to the fourth. And what those do, they do exactly what they do over there with the negative sign, right? They change positive, negative, and so on. So that's the reason why this is looping the way it's looping. But it's not a part of this course, but those of you that are, more thirsty for knowledge, there you go. I quenched that. Good. How about we find an equation of the tangent line, because we can. Find the equation of the tangent line to f of x equals e to the x, e to the x cosine x. Is this good? No. Oh, you're writing in pen? Too bad. X squared cosine x. No, I'm just kidding. At x equals pi over 2. So this line should really, really look bad if you do it correctly. Okay, let's take a look at this together. The procedure for tangent line is always the same. Your job is to take the derivative and then plug in point to find slope. So f prime of x must be the product rule because it is multiplication of a polynomial and trigonometric function. So copy the first times derivative of the second plus copy the second, which is cosine x, times derivative of the first, which is 2x. We are going to compute this to find the slope at pi over 2. Now, it's going to be pi over 2 squared times negative sine of pi over 2 plus cosine of pi over 2 times 2 times pi over 2. Now, cosine of pi over 2 is 0, which kills the entire second term, and we get that the slope and sine of pi over 2 is 1, so the entire parenthesis over here goes to negative 1, so we have that this is just a negative pi squared over 4. That's our slope. Y is f computed at pi over 2. Now, that's going to be pi over 2 squared times cosine of pi over 2, but that's 0. So I have pi over 2 comma 0 for the point and negative pi squared over 4 for slope. Let's plug this in into y equal mx plus b. Y is 0. Slope m is negative pi squared over 4. X is pi over 2 plus b. Now, this is pi cubed over 8. So b equals pi cubed over 8. So what's the equation? Y equals negative pi squared over 4x plus pi cubed over 8. That's it. That's the tangent line at x equals pi over 2. Obviously, as soon as you change pi over 2, the equation of the tangent line will change. Now, the challenge is, obviously, as you are working on these concepts at home, you fire up your graphing app and you graph both functions at the same time. Make sure that they touch at one point at pi over 2. Right, the function and the tangent line, if you carefully, plug this. Now, try not to use decimals, right? Use the pi squared and pi cubed, and the graphs should work out perfectly. And that's it. That's the derivatives of trig functions. You will have to memorize this box. It contains 6 derivatives for 6 trig functions. If you don't want to memorize that, well, obviously, you will be figuring out the sign this way and then cranking quotient rule for all other functions. See you tomorrow. We'll do 3, 6, 3, 7, right? Ooh, 3, 7 tomorrow. That's chain rule. Yeah, guys, that's 90% of your derivatives you are ever going to take is going to be 3.7. So, yeah, pay attention on 3, 7.
So only 3, 7?
3, 6 and 3, 7. 3, 6 is on a shorter side. So, and make sure you complete the first lab as soon as possible. So we might steal some time tomorrow to do some lab work. So have at least 10, 15 problems done for tomorrow on lab 2, if not all.
Lab 2 or lab 1? I mean, you know what I mean. The first